Where would this be something you would want to take a look at, where you want to take a look at the force acting on something at an angle? Downtown, you happen to live in a city that has a lot of these. You see buildings, and on the outside of the building, do they have signs saying, come eat here?
Yeah.
Do they have cables attaching the sign to it? They do. Go take a look at it. See how that would be providing a force holding the sign up at some angle? You're like, well, I'm not going to be a sign builder. Fair enough. If you go to the lacrosse center, if you look up in the top of the lacrosse center, or even in our gym or auditorium, but you'll see all this rigging or scaffolding up there, and then they got lights and speakers hanging up there. How do they support all that stuff up there? Wires and stuff at angles. Have you ever seen a bridge across the water that looks something like this, where it's got two big pillars in the middle, and then they have cables going out at different angles holding up the bridge? You might be thinking to yourself, well, I'm never going to do that stuff. And that's fine and all, but who's the person that designs this bridge, or the person that designs the scaffolding, or even the person who designs that? What sort of classes would they have taken in high school?
Physics.
And what class did you decide to sign up for?
Physics.
Okay, so yes, it does become way more complicated, but this is the starting point for it. So the question is, what is the tension in that rope? So find the tension in these strings that are in those wires. So let's go ahead, and those numbers are real. That is a 1 kilogram mass hanging up there, and I have a protractor sitting on my front desk. You can even still see my footprints on the front table of where I stood on the table first hour to measure it. Okay, so it is 67.5 degrees, and it's the same on both sides. What's going to be the first step in this problem? Step 1, free body diagram. Then go ahead and label our forces. So the first one's easy. There's a force of gravity. And can we do the math on that real quick? If it's a 1 kilogram mass, what would be the force of gravity acting on that thing? It's 1 times 9.8, which would then end up being 9.8 newtons. What do we call the forces in the ropes then? Tension force. Now it's going to get confusing if we say force tension, because aren't there two ropes? So what should we call it instead then?
Like X and Y or something?
How about rope 1 and rope 2?
Okay, that too.
Force of tension in rope 1, force of tension in rope 2. Time we did this before when we had an angle, what did we have to do? And isn't this one, since it's going over at an angle, isn't there also a component of this in the X direction? So this rope's pulling a little bit to the side. And to label that, we would say force of tension 1, X. And then what would we call the corresponding one in the other side? Force of tension 2, X. But the ropes aren't just pulling sideways, they're also pulling up. So then what you would have is a component for the Y direction. So that would be force of tension in the first rope in the Y direction. And then over here you would have the force of tension in the second rope in the Y direction. Has our drawing got confusing pretty quick? So this is what I recommend. Just redraw the free body diagram, only looking at the X and Y components. So go ahead and do that right now. Draw the free body diagram, but redraw it, but this time only include the stuff that's in the X or the Y direction. So gravity's still there. Force of gravity is still 9.8. Then what we're going to do is we're going to draw this one. So force of tension rope 2 in the X. Force of tension rope 1 in the X. And now take a look. We have force of tension rope 1 in the Y. Force of tension rope 2 in the Y. Now when I redraw it like that, does it make things a little bit simpler to see what's going on? First off, which two forces are going to cancel? What's the easiest one to see that they're going to balance each other out?
Are we recording this right now?
Yeah.
So they can hear me?
No, I'll edit you out. The X ones, right? Those two sideways ones, they're the only two forces acting horizontally, so we know that those two would cancel each other out. They're going to be equal in size, just opposite in direction, so they cancel. So is there really any need for us to take much look at them? No. Now take a look at the other one. What are the other forces that have to balance out? What would be the sum of the forces in the Y direction? So write the force equation here for the sum of the forces in the Y direction. The force of tension in rope 1 in the Y direction plus the force of tension in rope 2 in the Y direction. We would then have to subtract off the force of gravity since it's going in another direction. These two ropes, since they're at the same angle, what does each one of the vertical components of that rope have to be? What I'm trying to say is, which rope is pulling more? They'd be the same? Same angle, same rope. They'd be pulling the same. So if you think about that, here's another thing you can think about. Force of tension in the y direction for rope 1 is going to be equal to the force of tension in rope 2 in the y direction. Sorry for flipping this around. It was just a misspeak. I'll put it back in. Force of tension, rope 1, y direction. Those would be equal to each other. And so what we can do is we can substitute that in. And what will happen here is if I plug this in for this, then what happens is our statement goes to something like this. The question wasn't find the force of tension in the y direction. What was the question? Find the tension in the rope. So how do we do that? I'm going to give you an answer. It's not 4.9. And a lot of students are like, what? How can that be? Well, think about this. These ropes are pulling up at 4.9, but what also are they doing since they're at an angle? Aren't they also pulling against each other a little bit? So the tension in the rope is actually going to be greater than what they're supporting vertically. Draw for one of the ropes. So I'm going to do it for rope 1, force of tension in rope 1. And what do you now know about the force of tension in rope 1? You know that the vertical part is how much? The other piece of information that was given us in the problem where it starts to matter is this is 67.5. So do we have enough information to figure out what the tension in that rope is? Okay, the side that we know about is the opposite side in this triangle. So we would use sine. Sine of theta would be equal to opposite over hypotenuse. Or in our problem, it would look like this. The sine of 67.5 degrees is going to be equal to the opposite side, which is 4.9, divided by the hypotenuse, which we called the force of tension of rope 1. Now that you have that, it becomes very easy to solve if you have a calculator. 67.5, or 4.9 divided by 67.5 is 5.3.